Hello and welcome to Lecture 68 of my class From Data to Decisions. I'm Chris Mack, your instructor, and this is Factorial Design of Experiments. We've been on a series of lectures about the design of experiments. So let's talk about the process by which we do actually design our experiments. First, we define the objectives of the experiment. This may seem obvious, but in fact, sometimes we have hidden objectives we don't think too much about, and then we realize in the end that we didn't meet them because we didn't design our experiment properly. So thinking carefully about all of your objectives is important. Next, you define the inputs to the process as well versus the response that you want to measure. There are three kinds of inputs, as we've talked about several times. First of all, the controlled inputs. These are the things that we are trying to vary. We purposely vary them in order to measure or understand how they affect the response. They are completely under our control. But there are also uncontrolled inputs, and some of these uncontrolled inputs are measured, and some of them are unmeasured. The measured uncontrolled inputs we deal with blocking. These are the nuisance variables we deal with blocking or with covariate analysis. Uncontrolled, unmeasured inputs, sometimes we don't even know what they are, we try to deal with randomization. Our inputs, of course, can be continuous, things like voltage or current or mass, and discrete, such as using tool A versus tool B, factor A versus factory B, operators, etc. The controlled inputs in our experiment are called factors, and for each factor we have to define the range over which we want to vary it and the number of levels or the number of data points within that factor that we are going to take. Unfortunately, the process of designing an experiment has a certain circular quality to it. Our design means we're setting which predictor variables to vary, setting the range over which we vary them, and the levels, the distribution of the values, the sampling. Sometimes we call this a sampling plan. If we know what the response function, how the response function varies with our inputs, that is, if we have a model that we trust, then it's not that hard to decide how to sample. In fact, there's algorithms for doing it and what we've discussed before as optimal design. So we can apply one of these optimal design approaches and figure out the optimum way of sampling, assuming we know what our model is. But often we're doing exploratory work, screening experiments as we'll call them, where we're trying to understand which variables are significant, which ones are not so important, what ranges should we use, and what is the basic nature of the response. Is it linear? Is it nonlinear? If we don't know these things, it's very hard to figure out what the best design will be. And left with the sad conclusion that the best time to design an experiment is after it's over. Because only then do you have enough information available to actually do a good job of designing experiments. Well, I'm sorry, but that's just the way life is. You always have to do something a first time, and the first time you look at variables and how they affect a response, you might be surprised at what you discover. So you just have to understand, do the best job you can, design your experiment, but you may have to go back and do it all over again based on what you learned the first time. Which brings us to the topic of exploratory designs. If we don't have a very clear idea how the response is affected by our predictor variables or factors, then there's an approach that many people use to help us get there sequentially. We start with simple screening experiments to pick the variables and to investigate the range. We follow that up with more detailed investigation based on the results of the screening experiment. Instead of trying to do the entire design and experiment all at once, only to find out that we didn't picked the right variables or the right range, or maybe we wasted a bunch of time measuring in sample spaces that were not interesting. We break it up into pieces. We start with a screening experiment, maybe taking something like 25%, a quarter, about, of our data, and say, let's do screening with that. And then we add more data points later based on those results. We're going to see that a little bit more when we talk about response surface modeling in a coming lecture. So probably everyone has, if you're a college student and you're in engineering or science and you've gone and done some lab and some experiments, more than likely the way that we've thought about and the way we've actually performed our experiments is called one at a time variable change. So I pick a variable, temperature, and I change it over some range, incrementing it and making measurements. I pick the other variable, or its concentration, and I change that, and I vary that at a fixed temperature. Right? My temperature variation was at a fixed concentration. This one at a time variable change does not allow me to investigate interactions between these variables. So if they were completely independent of each other in their response, well, then this would be just fine, but that's not often the case. A design that samples, that varies both temperature and concentration simultaneously, can be both more efficient and provide some measurement of the interactions between these parameters. So that's what this design of experiments is really all about, getting out of the one at a time variable change approach that is a hallmark of very simple ideas about experimental design. And the most complete way of sampling our design space is the full factorial design. I have a number of factors, let's say A, B, C, maybe others that I'm going to use. So I'll call capital A one of the factors, for example. Then we've got some number of levels that we're going to apply to that factor. I'll use little a to represent the number of levels of big A over some range that I've decided upon. Factor B will have small b levels, and C will have the small c number of levels, etc. What we generally do to describe design is to assign the number -1 to the minimum value of that level, and the number +1 to the maximum value of that level, and then, of course, normalized in between. We call these coded variables. They're simply centered and scaled to the range, kind of like the normalized or standardized variables that we've talked about in the past with respect to regression. But here it's standardized with respect to range. Then we're going to perform some number of replicates. Maybe n is 1, but n might be 2 or 3 or 4, where we completely repeat the entire experiment, called replicates. If we were to do a full factorial design, and that means we're going to measure every possible combination of every factor, and we're going to do them all n times, the replicates. That means the total number of measurements is going to be n times A times B times C, continuing on for how many ever factors we have. This is a very popular choice because it does allow you to sample the entire space very, very thoroughly. However, if you have a lot of factors and you want to use a lot of levels, the size of the experiment can grow dramatically. Nonetheless, especially for a few factors, this is a very common design. And one common way that we use it is in screening experiments. In a screening experiment, we're basically asking, is this variable important over range that I'm going to try it over? So we pick a factor and we only run experiments at the min and max values. We'll label those min and max values -1 and +1, and we won't do anything in between. This is a 2-level full factorial design. If I have m factors, there's going to be 2 to the m experimental runs for a full factorial design, of course multiplied by the number of applications that I want to use. With this, of course, each variable direction, say x1 or x2, I can only detect linear variations. I can see if it's changing, but I don't really know if it's changing in a linear way or a complicated way. I can't see that. Detect a chain. But I can also detect interactions. All the interactions are covered here. One of the nice things about this design is it's completely orthogonal, so that there are no multicollinearity issues involved. Every parameter I can look at in a very simple way as being uncorrelated with all the other parameters. Very nice property of this design. We can add more data later as well. So later on we might say, ooh, x1 really interesting. Let me throw in some extra points in between the min and max range. I could even extend the range if I thought it was interesting to do so. And we don't have to throw away the old data points. We can add more data points to our design. We do typically want replications. Certainly replications help from a blocking sense, but also we use them to estimate the errors in each individual experimental point. Here, because we're talking about interactions, I'm going to pause and talk about something I probably should have mentioned in a previous lecture, but is an important thing to consider whenever we're doing modeling with either interactions or higher order terms. That is the hierarchy principle. I think I might have mentioned this before, but in model development, the hierarchy principle says you should only include a higher order term or an interaction term if the lower order terms that constitute that higher order term are also included. I'll give you an example. Suppose I want to have the term x1 squared times x2 in my model. If I put that in the model, the hierarchy principle says we should have x1, x2, and x1 squared all in the model before I put in, or if I'm going to put in, this combined x1 squared x2 term in the model. Now, it may turn out that not every one of those terms is statistically significant, and you may ask, why do I need all of these terms? Maybe this is the only one that really matters. And the answer is sometimes you might not. But the reason why many people rely on the hierarchy principle building models is because only hierarchical models are invariant under linear transformations. That sounds fancy, but it goes like this. If I were to shift where 0 is in my variable, do I get the same model other than changes in the specific values of the coefficients? If I were to change the units of temperature from degrees centigrade to degrees Fahrenheit, for example, you would think that I get just a change in the values of the coefficients because of the new units. Other than that, the model works just as well. It has the same relative standard errors and same prediction capabilities, etc. But that's only going to be true if models include all of the lower order terms. Now, sometimes you've got natural zeros. For example, temperature, if I were to use absolute temperature, then I wouldn't have to worry about this problem. But sometimes we don't have a natural zero. Sometimes we pick 0 to be just the value at the beginning, or maybe it's the value of the response at the plan of record, the process of record, the thing we're doing now, and we're trying to vary it. If we don't have a natural 0, then it seems very strange that if I were to change the units of one of my variables, that all of a sudden my model being a really good model to being a really bad model. And that can happen if you don't include these lower order terms when you do have the higher order terms involved. So, does the hierarchy principle mean that you always must include the lower order terms? No, it doesn't. But look at your variables. If you have a case where there's no natural definition of what 0 should be, and you want linear shift invariance in your model, which most of the time you do, then the hierarchy principle should apply. Note that the higher order and interaction terms often mask the main effects, so that sometimes it looks like the main effects or the lower order terms are not significant, really just being masks by the higher order terms. All right, that was an aside. I thought I needed to throw that in here because we're going to spend a lot of time talking about interactions. Let's consider a full factorial model. And let's suppose we have a lot of factors, in this case, 7 factors. And we'll do a very simple one, just a 2-level, 7-factor full factorial design. There's going to be a total of 128 runs. Now, when we look at this, we see that there's a number of interactions that we can extract information about because of the full factorial design that we've used. All right, there's going to be one overall average. Right? There's going to be 7 main effects, that is the effect of each variable by itself. But then there's a total of 21 2-factor interactions. And we could extract information about all 21 of those 2-factor interactions. There's going to be a total of 35 3-factor interactions, 35 4-factor interactions, 21 5-factor interactions, etc. And of course, 1 7-factor interactions. All information about all these interactions are present if we do the full factorial design. Well, it may turn out that we don't care that much about these higher order interactions. Maybe these 4-factor, 5-factor, 6-factor, 7-factor interactions are simply just not interesting to us. Often, those higher order interactions are very negligible. This is sometimes called the sparsity of effects principle. It just means that when you get more and more interactions together, they just stop interacting with each other very much, and the effects become insignificant. This gives us an opportunity. If, in fact, the sparsity effects principle is in play for our data, we can figure out a way to reduce the number of runs, the number of experiments we have to perform with a proper design, allowing us to get the main effects and the level of interactions we're interested in, but ignoring the higher interactions. We call this a fractional factorial design. Let's see how it works. The first thing, of course, if we're going to choose a subset of the full factorial design is how do we choose it? We want some properties for this design. We want the design to be balanced. We want it to be orthogonal. Balance means every combination of levels have the same number of observations. And orthogonal means that if I look at one factor and I sum up the effects of all the other factors, I see that they sum up to 0. And using the -1 +1 labeling that we use. So we want balanced and orthogonal designs, and that limits how we might remove data points from a full factorial design. In fact, it means we have to eliminate them in a certain symmetrical way, like eliminating half or eliminating 3/4. We can't eliminate, say, 1/3 of the data points, leaving 2/3 behind, and get both balanced and orthogonal designs. But we can get a half factorial design or a quarter factorial design and achieve these goals of balanced and orthogonal. Here's an example of a half factorial design for 3 variables. 3 variables are x1, x2, and x3. In a full factorial design, I would graphically display a point at the corner of each corner of the cube. That would give me every combination of x1, x2, and x3 the two levels, +1 and -1. So a half-factorial design would remove half of those points. But the way you'd remove them is by looking at these opposite corners being removed. So now I have 4 points left and 4 points removed. Of course, there's two ways to do that. So there are, in fact, two different half-factorial designs. These half-factorial designs are balanced or orthogonal. They have an extra problem associated with them. The main effects are going to be confounded or aliased with the two-factor interactions. I'll talk about what that means with an example next. Let's design two-level half-factorial design, and I have 4 factors. So a full factorial design with 4 factors would have 2 to the 4 runs, or 16 runs. So a half-factorial design would have 8 runs. How do I design a half-factorial design? Well, I start by designing a 2-level full factorial design for 3 of the factors. Doesn't matter which 3 you pick. I'll pick x1, x2, and x3. So let me put together a table of those 3 and do a full factorial design. Well, that means there's going to be 2 to the 3rd, or 8 runs, and we can easily see that the first column I do -1 +1, -1 +1, -1 +1. Second column I do in pairs of 2, -1 -1 +1 +1, etc. And the last column I do 4 -1s followed by 4 +1s. Just a simple way of generating your full factorial design. And you see that every possible combination of x1, x2, and x3 are found here. Now, the 4th column, x4 for the 4th variable, I generate as the product of the previous 3 variables. So in other words, I make x4 equal to x1 times x2 times x3. So here, -1 times -1 times -1 is -1. +1 times -1 times -1 is +1, etc. And I do that all the way down, and I get the values I need for x4. This is how we achieve our 2-level half-factorial design that is balanced and orthogonal. Now, the alternative design is just to throw a minus sign in the equation, so there's always going to be 2 options for creating this half-factorial design. One of the problems with half-factorial designs, so in any fractional factorial design, is aliasing or confounding. Right? Here's that 4-factorial design that I just showed you on the previous slide. So we designed it all up, and boom, we have it. Now, suppose we wanted to have x1 times x2 in our model. So we wanted to include this interaction term in the model. Well, what's x1 times x2? We can just, x1 times x2 is +1. There you go. How about here? x1 times x2 here is -1. Boom, there you go. So we can easily calculate what x1 times x2 is for every experiment. Now, do the same thing x3 times x4 interaction. If I wanted to include x3 times x4 as an interaction model, well, I calculate those, and look what I find. They are exactly the same values as x1 times x2. With this fractional factorial design, I cannot distinguish between the x1, x2 interaction term and the x3, x4 interaction term. They look identical. And what I measure will be a combination of both of those interactions. In other words, that interaction is confounded, aliased into one term that includes both interactions. So remember, these are physical things. And if these physical things really do interact, right, they'll affect my results. But if x3 and x4 are interacting with each other, it will affect the response in the exact same way as x1 and x2 interacting with each other, and I can't distinguish them. All right? The same thing is true for x1 times x3 confounded with x2 times x4. So this kind of confounding or aliasing is a consequence of using a fractional factorial design rather than the full factorial design. With the full factorial design, we can easily separate out these terms. All right, one other interesting topic I want to mention, projections. Suppose you did a half factorial design as a screening experiment, and you wanted to determine whether the variables x1, x2, and x3 are significant, or which of these variables are significant. Suppose that one of them turns out to have no effect on the response, so x1 doesn't do anything. I vary it, and nothing is different. X1 is varied. All right, that's something we learned. I don't need it. Well, if x1 has no effect, then I can collapse my half factorial design. I can project the x1s as being identical with each other down to now a full factorial design. So if I have a half factorial design, but one of the factors turn out to be unimportant, it will collapse to a full factorial design, and then I can do my analysis under that assumption. So always look for the possibility of collapsing your half factorial design into a full factorial design. Finally, these screening experiments, if we have a two-level factorial design, whether it's fractional or full, we only look at the plus and minus points. But there is a middle to the entire process space. And often we add that center point as well, usually with repeats. Sometimes we have to do this as a conscious thing. Let's say, all right, let's go to the exact middle of my design space and make repeated measurements there. But sometimes we don't have to, because a common way of applying the design of experiments is to say, I've got a process, maybe it's my manufacturing process, I'm running it all the time, I've got lots of data, historical data, I make measurements on my center point process all the time because it's the plan of record, it's the process that I run on a daily basis. I mean, obviously I'm talking about situations like you're in a factory or you're in a fab where you have a process that's running on a regular basis. So you might have a significant amount of data about the plan of record already. If that's the case, you can design your experiments to be symmetrically displaced plus and minus about the center for each of the variables that you want to study. And that way your center points kind of come for free. But in any case, you may decide to go and measure them as well. The nice thing about using the exact center points for your design is it does not affect the orthogonality of the design. That means it won't change any of the model parameters. If I make a bunch of measurements and stick those measurements into my model, all the coefficients remain the same, except one, the overall mean, the beta zero, the intercept term of the model. Well, this is very nice for this reason. But remember, our model only has linear terms in it. We can now use center point to check the validity of that assumption that linear terms are all we need. You can go look at second order terms and ask if they're statistically significant. And that can guide you next step. All right, what have we learned in Lecture 68? Factorial designs are very important, very commonly used in industry and in science as well. What is full factorial design? What kind of design is often used for screening variables? What is the hierarchy principle? What is fractional factorial design, and what are its advantages and disadvantages? And explain aliasing in fractional factorial design. We still have some more interesting topics to go on the design of experiments. Till then.